So welcome back, guys. Today we continue with the three good bases, and mainly we'll talk about the CZ interpolative decomposition, and we'll move on to the CMR decomposition or factorization. So remember last time we tried to use that exact first factorization we've used in the beginning of the semester, where we wrote A equals to CR. And remember, C was composed of independent columns of A. Okay? And R, in fact, was a matrix that mapped let's say the way you're going to use these independent columns to get back to A. Okay? So in fact, we are starting from that point exactly here. And in the next part, what we are going to say is that this is equal to, let's say it's equals to CZ, okay? So for instance, now let's assume that R is exactly Z, okay? And the first thing we are doing here is that we are assuming that, it's exactly here, we are assuming that C is equal to YB, okay? And if you assume that C is equal to YB, where B is the submatrix of A, then there is a way to write again A as Y times B, okay? And B is a square submatrix, as you see, okay? With, of course, dimension. So we can show that in that case, Y could be written as AR, IR, which is the identity matrix of dimension R, and the remaining rows could be obtained from B using CM minus R times B minus 1. Now, what is CM minus 1? Okay? Remember, this calls back CMR, okay? So it is telling me that these are the remaining rows in CMR when you already used all first R rows, okay? And we'll see just in 1 minute or two how this would be obtained, okay? And the next part is to show in that case that if you are able to write C as YB, then in fact you can write Z using the previous Z, okay? Which is going to be YR times B minus 1 Z n minus 1. So I'll start again with the same with the same example we had. Okay. So here, first of all, we what did we do here? We used first of all this column, which is taken exactly from the first column. Okay. Now, if you look at it, this is exactly what we called I index R. Okay. Now, what is left is how to obtain the remaining row. But if this is B, as you notice, is this submatrix of A. Okay. Now, what is B minus 1? B minus 1 will be equal to what? To 1 over the determinant of B. The determinant of B here is just 1. Okay? Times, well, it's easy to obtain as an inverse matrix. It's going to be 1, negative 2. That is a jump in there. Okay. And right. So it's basically 1 times 1, negative 2, 0. So now what is left when we took this part from C, which was supposed to be 101 to 13, is just this part. Right? Okay. So to obtain this 1, 1, in fact, what we did is just a multiplication of 1, 3 by B minus 1. Okay. So this is exactly Cm minus 1. Cm minus 1. Okay. So let's check if it works. It's 1, 3 times 1, 0, negative 2, 1. All right? So what you guys get is 1, and on the other side it's going to be minus 2 plus 3, which is 1. Okay? So this is the way we got this last row. See it? It's here. It's 1, 1. Okay? So now that we filled the matrix Y, as we said at the beginning, it is composed of YR, and this part is just Cm minus R, which was here, identified, and it's taken directly from A. I mean, this is the part that is left when you took these two columns, 1 and 2. You used the upper part in B, and the remaining part you have to use it with Cm minus 1. Okay? So if you multiply it by B minus 1, you will get 1, 1. Okay? So this is what has been obtained. Now, to update Z, okay, we use the formula. Now, the remaining formula said that you will place IR, okay, then it's B negative 1, Z n minus R. What does that mean? It is the remaining R when you've taken the two first rows, okay, or the two first columns. Okay, now, so this is the IR. Okay. I've shown you how to complete now. So they said that this is Zn minus R, okay, times B minus 1, if I'm right. Let me check the last time. B minus 1, Z minus R is the opposite. Minus 1, Z minus R. Z n minus R. So we've just computed, in fact, B minus 1, and we found out that it is equal to how much? To 1 over 1, 1 with the derivative B, and we found out 1, 1, negative 2, and 1 is 0. Okay. So from where do we bring these two columns? We said we brought them from the previous iteration. What was the previous iteration exactly? The one that used the capital R, right? Yes?
Yes.
And what did we write? Yes. What did we write? Okay. If I had to use 101213, yeah, I would have written here R for me. So if C was equal to 101213, what would be R? Now let's notice here. The second, why the rank is 2, because the third row is twice the second row. Okay? So basically, I will place here 1, 0, after 0, 1, as it appears here. Of course, you have 0, 2. Why? Because it's twice the second row, and you have 0, 1. Okay? You see exactly, you already have this, which is red. Okay? If you want to check more, multiply it by B minus 1. It's exactly, you'll keep exactly the same thing. Okay? Now, the question here is what happens if you want to improve the choice of B. If you follow the slides, we want to improve the choice of B such that the norms here, or the absolute values of the Yij's and the Zij's could be less than 1. So we want the determinant factor of the submatrix B we are going to choose to be the largest as possible. Okay? And one of the last thing we've seen last time is that if you focus again on this matrix, let me change the colors. If you focus again on this matrix, well, if you want to choose the best columns, I mean those who are going to give you the submatrix B with the highest determinant, B max would be composed of these two, in fact, taken from these two columns. I mean, B max would be 1, 0, or 2. Because the determinant now is not 1 anymore. The determinant of B max is 2. Okay? So the question, what happens if I'm not using anymore this B? I'm using a new B. I'm updating B. Okay? There would be changes. And there would be consequences. Okay, so I will use exactly what I've used before. So I have to find a new reverse. Okay, I'll update this code, and I'll have to update some parts here in the Z, right? Okay. So, let's focus on the updating of the Z first of all. Okay. Should I use the whiteboard if you wish? Yeah. I'll go back to the. I'll use the blackboard if you wish. I'll write here. Maybe it's better to write here. Okay. So to update, I mean, you have to think now. To update the Z, I have to place a new matrix here. 1, 0, 4, 2. Such that if I multiply with the new Z, I will get exactly the same part which is here. Okay? Forget about Y, for instance. Let's decide to keep the same Y. Okay? Keep the same Y. Now, for sure, I'm going to have 1, 0, and here 0, 1. Why is that? This is the YR, which maps, in fact, the fact that now you're not choosing the first and second columns anymore. You're choosing the first and third column. Right? You get it? You get this point, guys? Now I have to write the IR should be divided in two columns, 1, 0, and 0, 1. I mean, here, this is the third column. What is left is what should be here and what should be here. Okay? And this is, if you collect them together, you're going to have the IR. Okay? But between, you are placing something. What are you placing? You have to solve a system. What is the system? The system that will tell you that once you multiply 1402 by this column, okay, you have to get the 0, 1 you got before. Okay? You have to get what did we get before? Here. We have to get the 2, 2, 1. Which 2, 1? The 2, 1 that was here. Okay? Right. So let's solve it. I'm going to multiply 1, 0, 4, 2 by some column. Let's call it. This is going to be Z2. Okay? And let's find out 2, 1. Okay? So here, the Kramer rule says that the components here of Z2 would be obtained by the determinants, in fact, formula. The first one, let's call it Z21. I'll write it in the board. Z21 here would be the determinant of 2, 1, 4, 2. Here I placed that column I wanted to find here inside B over the determinant of B max. Okay. And I find out that it's how much is the determinant upper determinant here is 4 minus 4 is 0. And here I'll have the determinant of B max, which is, so I'll get C. So this is for Z21. Now for Z22, so I found out, I'm finding out the two components of the second column. I will try to find now, I'll take the first column of B max, but instead of writing 4, 2, I'll write that 2, 1, I want to retrieve. Okay? Divided by the determinant of Bmax. And here we get the 1/2, which is 0.5. Right? Okay. So this way, we got these two items, which are going to place it in Z. So we map exactly the results of the change on our matrix set. Let's go to this part again. So these are this is the 0 and 0.5 we just found. Now the last part is exactly the same, because in fact you are trying to retrieve exactly the same column. Okay? So that's why it's going to be the same. Okay? So this is for how the A now written as YB max Z instead of YBZ. Okay? Why is that important? Yes, Abdullah.
Why is it negative?
Yes. Okay. Why is it negative? We found 0.5, right?
Yes.
Okay. How much was the determinant? It was negative or positive. So let's do it again. Vmax 0 or 2. So my determinant is 2, which is positive. And the submatrix I'm supposed to have supposed to retrieve. If I keep the same y, I get 1, 0, 1, 0, 1, 1. Okay. Here I'm placing I get 1, 0, and 2, 1. Okay. Previously, when I multiplied by the second row, by the second column, how much did I have in the previous slide? So I don't want to change it here. Let me open it on the other side. Let me just try not to lose it, okay? It was the second row, and the previous Z was, how much was it? It was 0, 1, yes. It was 0. So, how much is it times 0, 1? Let me just multiply it by 0, 1. How much is that? Let me multiply this B by the 0, 1, which was previously there. It's supposed to give me 2, am I right? And 1. Okay. So now this is what I want to find. I want to find Vmax times the new row equal to 1. Okay. So let's take it here. So I'm going to have Z 1, which equals the determinant of Bmax, but instead of the first row, I'm going to put 2, 1. It's 4, 2 over the determinant of Bmax, which is 2. And this is going to be 0, as you see. Okay. And the next component is Z2, 2. And instead of the second column, I'm going to put the 2, 1. I mean, instead of the second column of Vmax, I'm going to put 2, 1. And have this. And I ended up with half it. So I did it several times. I have no idea why is it minus 0.5 in the textbook. So I just wanted to check again. I did it. This is the third time I do that. I think it's a typo, but I'm not sure. I checked with the 0.5. It worked. I have no idea why is it minus 0.5. Okay. Maybe it's just a typo from part, but in the textbook it's minus 0.5. So let's summarize. Okay, let's summarize and let's take something. At least valuable from this. Since we are keeping the same y with the b max, which would be placed here, and multiplied by the new column, I need to find exactly what I found when I multiplied the old b by the old column. Okay, so I have to compute the old b by the old column and just solve the system. Okay, so let me write it again on the whiteboard. The system that I'm gonna solve. Okay, so for every column, we're trying to compute. Let's call it ZG times the new B max. We are trying to find the old B. So let's say this is the new column times the old column ZG. Okay, this is how we solve it. For instance, in the old B, let's say the old B was, let's say this is it, okay? It was like this. Doesn't matter. Any other example, okay? This is the old B, and this is the new B. B max. Let's say this has a larger determinant, for instance, and this is like, right? So let's say that the old ZG was equal to 1, 1. Okay? So the new ZG solves this system. 4, 1, 0, 1 equals to B times the old ZG, yani 2, 1, 0, 1 times 1. So this is your limit system. 2, and I think it's going to be also 2. Okay? So this is how you get the new column ZG. Okay? Is that okay, Abdillah? So this is, I did it like 3 times before. I got halves and halves. I didn't have 105. I was hoping to get again an idea what came from, but I'm thinking it works with 0.5 just fine. Okay. So let's move to the new factorization, which is the CMR factorization, which in fact it builds on what we just seen, but hopefully it's going to be much more clearer. And basically the idea is much more clever. So this is the new slide, and the only new slide we have for today. Here, so with the CMR factorization, the goal is to find now a mixing matrix we call M, such that A equals CMR. In fact, we generally assume that for large or low rank matrices, we have to accept the idea that we are not going to end up with an exact factorization. Right? So A is approximated by CMR. Okay? So let's see what happens mathematically. Hopefully we can focus on this, guys, so I won't have to repeat it. So if we could focus on this, I will be able to solve 1 or 2 examples with this. So are you ready? So if you suppose that you have A equals CMR, one can write the following. If you multiply the both sides by CT, you're going to keep exactly the same equality, right? So if you multiply it by CT, also, and you multiply from the left by CT, you can also do the same and multiply from the right by RT. Okay? Got it? So what happens here is that the multiplication from the right by RT happened. Wasn't so. So, but instead I gathered the CT and the C together, that is the same brackets, and the R and the RT together. Okay? So hold on a second, I can tell myself, look, if I multiply now by RRT minus 1, so the inverse of this matrix, probably I can remove it from the right side of my equality. So this is exactly what happened here. I multiplied CT-ART by RRT negative 1. Okay? The inverse of RRT. So this guy disappeared here. It's no longer here. Gone. Okay? And I do exactly the same thing with the CTC. Multiplied by its inverse. So I multiply now by the inverse of CTC from the left. So on the right side now of my equality, I have this mathematics that emerged and n is left alone. So this is the way to get n. Right? So at the end of the day, you end up with m equal to what? CTC minus 1, or inverted, times CT, times ART, times RRT negative 1, or RRT inverse. Okay? Well, these two parts, in fact, that would appear here, this part is called the left inverse of C, and the other part is called the right inverse of I. Okay? And in fact, as you see, M would depend heavily on the choices you make on the columns you are extracting from A, and the way you're mapping R, of course. If you change R, you're going to end with a formula which is much more smarter and much clearer than what we've seen with the BYZ factorization. Okay? You have just a formula to apply. Okay? So let's work on this guy is supposed to be 1, 3, and it's 2, 4, I think. 2, 4. Okay, so let's work with this example and see what happens. So if I'm writing it as A equals to, first of all, I can write it like with the usual CR factorization. Okay, I can write it as 1, 3. Okay, and you notice that this is a rank 1 matrix because the second column is exactly twice the first column. So I can basically use one single column and multiply it by how much it is 1, 2, right? Is that okay? خلاص.
Yes, better.
طيب. Are you still alive, guys?
Yes, yes.
How many guys are still alive?
2 or 3.
So, okay, so alhamdulillah. Okay, so let's think for a minute that we don't like this R. I'm going to change it. What happens to the factorization? Okay, I'm going to write 2, 4. Okay, hold on a second. I have a way to get M exactly using this beautiful formula. What is it? It's CTC negative 1 times CT times A times RT times RRT negative 1. Okay? So this is what's going to happen. So I did the computation here. I found half. Let's do the math. Okay? So I'm taking my stuff and I'm doing it. I'm doing it with you. So just let me take note of these beautiful matrices. I know you hate them now, but you don't have the choice. Okay, and for me, CT is 1, 3, and R is 2, 4. So let me take them to my whiteboard. Okay, so okay, so let's work in purpose. So to me, A is again, it's 1, 3, 2, 6. Not easy to teach this physically. Then teaching it in remote. So this is C, guys, to me, right? And to me, R is 2, 4. Okay? So what did I say I need? First of all, I need CTC. So how much is CTC? It's 1, 3 times 1, 3. So basically, you end up with 7, which means that CTC inverse is ماشي ذات يا وين فراس؟ 1/10, yeah. Okay, now what else do we need? We need to compute RRT. RRT. That's writing well. So RRT is 24 times 24. So we basically end up with 20. Okay. RRT inverse is 1 over 20. Okay. So these are the only two complex things we. So the formula, what did it say? The formula said M is equal to CTC inverse, okay, times CT times A times RT times RTR inverse. Okay? So if you plug here, you're going to end up with 1 over 10. Here between, at the end you get the 1 over 20, sorry, 1 over 20. And between you have CT, which is 1, 3, times your matrix, 1, 2, 3, 6, and RT, which is 2, 4. 2, 4 in count. So let's see what we have. First of all, you see you have now, let me write this equation here. So I have 1 over 200, and when you multiply 1, 3 by 1, 3, you get 10, and the 1, 3 by the 2, 6, you get 2, and 18, so 20. And multiplied by 2 over 4. Okay? So at the end of the day, how much, guys? I have 100, because I have 10 times 2 plus 20 times 4 over 200, which is 1 half. Okay? So basically, what I'm just saying now, I'm saying that A could be written as, well, the first factorization didn't use M. Okay? It used just basically the fact that column 1 was independent, and column 2 was twice the column 1. So it used 1, 3, 2, 6, sorry, 1, 2, 1, 3 times 1, 2. And for this second factorization, now we are writing it as 1, 3 times half. Right? This is M to us. And times the new R, which was updated, which is 2, 4. Got it? Okay? And this example was specifically chosen to be able to inverse matrices of just one dimension, so nothing complicated. Okay? Is that clear, guys?
Yes, clear.
Now, of course, you have to think that if you are dealing with matrices with larger ranks, okay, the mathematically the formula applies, okay, and you can work on it. So let's close with another example. So that was my target. Let me take another example, and I have something for you. Okay, so I have this matrix. So let me, I'm taking an easy matrix, okay? And to me, this is 2, 1, 1. This is the second column, okay? And this is the first column, 1, 0, 0. And the third column to me is just specially chosen to be column 2 minus column 1. Okay, so it's going to be 1, 1, 1. Okay, easy. So directly, I know that A equals CR. For me, will be written as, how do we write it, guys? You could write it as, if you want to pick either column 1, column 2, or column 1, column 2, or column 2 and column 3, whatever you want. So basically, I can choose column 1, column 2, and what should be R now? I'm going to have 1, 0, 0, 1, and here I'm going to have minus 1. Am I right? Is that okay?
Yes.
Yes.
Yeah, okay. So let's say for a while, I don't like this R. I'm going to change it, okay? So someone told me Now, look, your R is now this one. So let's make the change not that difficult, so we can. Okay, so let's say this is the mapping that should be used. Okay, so let's say it's inverted. I'm gonna write something of this type. Okay, 0, 1, 1, 0, and 1 minus 1. Okay? I'm gonna write something like this. So immediately I have to seek what is M. So the C didn't change. So let's compute CTC first of all. So it's 1, 0, 0, and it's 2, 1, 1. Am I right? Times 1, 0, 0 times 2, 1, 1. So you end up with a 2 by 2 matrix, which is expected. We need a 1, a 2. Of course, it's going to be symmetric, of course, and this is the beauty of the thing. And you're going to have the last item is 4 plus 2, I think, which is 6. All right? So your inverse, the determinant here is 6 minus 4, which is 2. So CTC inverse, which you need anyways, is 1/2 of this matrix. 6, negative 2, and 1. Okay? So I just found CTC minus 1, which was the part I needed for M. And now I compute RRT. And how much is RRT? I have to multiply this new R by its transpose. It should be 0, 1, 1, 0, and I guess it's 1 minus 1. And I end up with a 2 by 2 matrix. So I have 2, then I have negative 1, I think. Then I have a negative 1, and finally I have 1 plus 1, which is 2. So the RRT inverse is equal to, how much is that, Shabbat? It's 4 minus 1, which is 3. So it's, you divide by 1/3, and your inverse would be 2, 2, and 1. Okay? So I found the two inverse function, inverse matrices. So I said at the beginning that at the end that this is how I'm going to write M. It's CTC inverse times CT times A times R transpose and times RRT. Okay? And now we just have to do the math. Of course, you see you have 1/6 that gets out, and you have a couple of matrices to place. First of all, I'm going to place 6 minus 2 minus 2, 1. Okay. That part is done. Now I'm going to put CT, which is how much? 1, 0, 0, 2, 1, 1 times A. So A between is 1, 0, 0, 2, 1, 1, and 1, 1, 1. And finally, you place RT. RT here is given as 0, 1, 1, 0, 1 minus. And the last part is just to complete this. Okay. Can you do the math, guys? Yeah. So probably, yes. So you're gonna have a 2 by 2 matrix. Huh? This is 2 by 2 times 2 by 3. You start with 2, you end with 2, so you're gonna have a 2 by 2 matrix. That should be. So we end up placing the 2 by 2 matrix between C and R. So that part should give you, I guess, should be 2 plus 1, 3, and I have 0, 2, and negative 1, and finally I have 0 plus 2, and I have negative. So you multiply it by this guy. So let me write the result here. I have we have 3. I have 3. There you get 0. There you get 6 plus 4, which is 10. And finally you get minus 2. So this matrix is the result of this whole part, okay? Just basically between 2 and goes down. To get your m, which is 1 over 6 times 6 negative 2. You can later on check the result. 3, 10, and 0, negative 2 times 2. The importance is not in the final outcome, but to know how to do it, okay? So we can finish it later on once we have the problem. So this is for the CMR factorization. This is like the last factorization we have. The next item I'm gonna see would be section 3.1. We'll start this inshallah after tomorrow, and it talks about how small changes in A impact the inversion of the matrix. And basically also I'll talk about what we call the Kalman filters, which is one of the most important concepts we see, or filters we use with, in data science. Any question, guys, before we leave? Did anyone reach any solution here? Abdulaziz, Firas, Abdullah, Abdullah. No one? Okay. So that's it for today. If you want to finish it, let's do it. Okay. I can do it here. I'll finish it here. I have 1, 6, and I have 18 minus 20 minus 2. Yes, Abdulaziz, how much?
0, 1, 1, 0.
0, 1, 1, 0. So this is like yeah.
After multiplying by 1 over 6.
Yeah, of course. So because we inverted the mapping, it was expected. So it's like an entire identity matrix. So it's minus 6 plus 10 is 4, and I have minus 2 multiplying 2, 1, 2, and 1, 2, and finally I get 1, 6. Here I have, how much is that?
6, 6,
6, 6, 0. This is the entire identity matrix, which is 0, 1, 1, 0. Beautiful. Thank you, Abdulaziz. So we have the right answer. Okay. So it means if you here placing this R instead of the previous one, this is how you map your impact, how the M is inserted. Now, of course, the choice of R here is easy. Okay, but imagine that the choice of R is messed up. Okay, and there are ways to develop on what is the best M to find that makes the approximation for large matrices works together. Okay? So that's it. Thank you guys for following. Sorry for any mistake or misconception. Well, we try our best, but sometimes not obvious it's a current situation. Okay, if you have any question, please let me know. I'll upload the slides for the 2.3 section. Next time, inshallah, we'll start 2.1. Assalamu alaikum.
Victor, there's no 2.4.